Okay, so just let's make a table. So we have I think it's not very visible. Okay, so we have the Laporte selection rule, we have spin selection rule, and then we have the type of spectra, we have molar absorptivity coefficient, and this last we have examples. Okay, so let's start with the one which has both allowed. That means it is Laporte selection rules allowed also, and at the same time spin selection rule allowed also. So most often this is the charge transfer spectra. Okay, the molar absorptivity is in the range of 10,000 centimeter inverse, and examples include MnO4 minus, CrO4 2 minus. Okay, next is Laporte selection rule is partly allowed. That means those having some PD mixing. This is still allowed. So if there is some PD mixing, this is the case of DD transition, and the molar absorptivity is now in the range of 1000. Examples include COCl4, this is 2 minus, NiCl4 2 minus. If you see, these are mostly tetrahedral complexes. Next is forbidden Laporte selection rule, but spin selection rule is still allowed. Okay, that would mean this is again DD transitions only, but which does not involve any PD mixing. This is of the order of hundreds. This would include examples like TiH2O whole 6, this is 3 plus, and cobalt H2O whole 6, this is 2 plus. Let's say the Laporte selection rule is partly allowed and the spin selection rule is forbidden. That means this transition would involve some change in the spin multiplicity. This is again the DD transitions. This is obviously in the order of 10. Example would include, as expected, manganese. Okay. Lastly, coming to both selection rules being forbidden, and this is most often less than 1. Okay. An example would include again manganese, this is water, another one being iron in its +3 state, which is also D5. Okay, so as you can see, the order of the molar absorptivity decreases down the group, so the intensity also decreases going from top to bottom. Okay, so I think that's all that is there to discuss about the selection rules, color in electronic spectra. Okay, so we have not done the charge transfer spectra, that we'll do in the next lecture. Now we'll start with the questions which are there from NET, GATE and TIFR for these two sessions, that is color spectra and the selection rules. Okay, so the first question we have is from GATE 2000, and the question says the complex which exhibits lowest energy electronic absorption band. Now, what are the examples you have? Okay, so I'm just writing the ligands. One has Cl minus, one has water, one has cyanide, another has cobalt. Okay, carbon. So lowest energy electronic transition would mean the DD splitting is lowest. That would mean DD splitting is lowest in the case of weak field ligands. This being the weak field ligand, the answer should be A. Since it is talking about absorption band, we'll look at the splitting of the d orbitals. Okay. The next question we have is from GATE 2003. The question says the number of absorption bands observed for FeF6 3 minus and COF6 3 minus. Now in the case of FeF6, this is at Fe plus 3, so that would mean this is D5, this is at plus 3, this is D6. Now for D6, how many transitions can we have? Now for D5, this being a weak field ligand, any transition would make delta S not equals to 0, so that is not allowed, so there are 0 transitions allowed for this. For this one, so there is, if I am not wrong, okay, there is one transition allowed from here. My mistake. I am extremely sorry. I mean, this is fine. So this will be 0 allowed transitions, and this should be 1 allowed transition because the other one would involve some change in the multiplicity. So there is 1, which is given in your option number B. Okay. What is the next question? The next question we have is from GATE 2002. Is it? Yeah. So the question says the lowest energy DD transition in the copper 3 complexes varies in the order. Now you have copper 3 complexes or octahedral complexes. The ligands you have are Cl minus, H2O, ethylene diamine, and cyanide. And if you can figure it out, it's written in the form of increasing ligand field strength. So the lowest energy DD transition should obviously for this, followed by this, followed by this, followed by this. That is given in your option number A, which is the correct option. Okay. The next question you have is from GATE 2011. So the question says the crystal field stabilization energy value for TiH2O whole 6 3 plus. That has an absorption maxima at 492 nanometer. So what is the CFSE for this? Now this being plus 3, that means D1. So that would mean it can do this transition and the value of the transition is delta O. 0.4 delta O. So this is 0.4 delta O is equals to 492 nanometer. Now if you want to find the crystal field stabilization energy in centimeter inverse, so delta O will become 492 by 0.4, and for this to, in terms of nanometer, for this to be in centimeter inverse, you just have to take the inverse of this. That would mean 0.4 by 492 nanometer. For centimeter, this will be 10 power minus 7, which goes up 10 power 7. This should, if I'm not wrong, this should be 8130, which is given in your option number B. Okay. The next question we have is from GATE 2011 again. And the question says the increasing order of the wavelength of absorption for the complex ions. Again, these are all octahedral complexes. We just need to look at the ligands. And finally, CM. So you have to write the increasing order of the wavelength. Now, energy is inversely proportional to wavelength. So the increasing order of the wavelength will be decreasing order of the energy. So if you want to look at the decreasing order, we must start from the strongest ligand. So that would mean it should be 4 less than 1 less than 3 less than 2, which is given in your option number C. Okay, the next question we have is from NET June 2011, and the question says the complex that absorbs light of shortest wavelength is, and you have again fluoride, water, ammonia and oxalate. Now the order for this should be, okay, so the shortest wavelength will be for the ligand having the highest splitting strength, which is for ammonia. That would mean the option number C. Okay. So the next question we have is June 2013. So the question says the electronic transition responsible for the color of the transition metal ions. What options do you have? D pi, D pi, D pi, D sigma star. So you have D pi, D pi, D pi, D sigma star, D pi, D pi star, and D sigma, D pi star. Now D pi, D pi is not going to happen because they have the same symmetry with respect to center of symmetry. D pi, D sigma star is a very high energy transition which will not fall in the UV visible range. The same goes for D sigma to D pi star. D pi star, and at the same time, this is Anjarade, this is Anjarade, this is Girarde, this is Girarde. They are not allowed. D pi star is Anjarade to Girarde, and they are going to be allowed and they are going to be colored. So that is given in option number C. Okay. Next we have June 2013 again. Intense band at 15,000 centimeter inverse in the UV visible spectrum of Bu4N whole 2 Re2 Cl8 is due to the transition. Now there is no way to actually figure this out without knowing the property of this specific complex. So you just have to memorize this. It can't be helped, but these kind of questions used to come. So in this case there is delta bond, and the transition is basically because of the delta star transition. Okay, that is given in your option number B. Okay. Then you have from December 2013, which says the oxidized form of the enzyme catalase prepared by the reaction of porphyrin with H2O2 has green color because oxidation state of the iron changed. No, it does not changes. Porphyrin ring is oxidized by one electron. That is true. H2O2 actually oxidizes the porphyrin ring. Pi star transition appears in the visible region. Fe4 is it Fe4? Okay, so iron is coordinated with anionic tyrosine ligand. Okay, so that is not also the reason. So either it could be porphyrin ring is oxidized by one electron, or it could be that pi star transition appears in the visible region. The correct answer to this is porphyrin ring is oxidized by one electron, which is given in your option number B. Okay. The next is from June 2014, and the question says COL6 3 minus is red and COL6 3 plus is red in color, whereas COL6 3 plus is green. So you have L and you have L dashed. This is red, this is green. You have to say which one is NH3 and which one is H2O, and there is another given for 1,10-phenanthroline. I'm not going off for that. Okay. Okay, so if you remember the color wheel, and going from violet to red, the wavelength increases, energy decreases. Okay, fine. So if this is red in color, that would mean this absorbs green, and if this is green in color, that would mean that this absorbs red. So let me write in a different color. That would mean this absorbs green, this absorbs red. Now energy for red is lower than energy for green. So that would mean the red is lower in energy than the green. So that means the splitting in the red absorbed is lower than the splitting in the green absorbed. That would mean the red one is water and the green one is ammonia. So the water goes for L dashed and ammonia goes for L, which is given in your option number A. Okay. The next question we have is okay, so the DD absorption band of, okay, so this is from GATE 2010, and the question says the DD absorption band of FeH2O whole 6 2 plus is allowed, is split. It is split due to, okay, so we'll do this when we do the, I think it should be done when we do the orbital diagram. That will be much better. Okay, next we have from GATE 2016. The question says in the first row high spin transition metal complexes with D5 and D7. So we're talking about high spin D5 and D7. Now it says that the first row high spin transition metal complexes with D5 and D7, the DD transitions are, for D5 obviously it is spin forbidden and this is spin allowed. So that is given in option number C. A very straightforward question. This is from June 2016. It says Ni2L6 shows absorption bands at, so you have L and L dashed. This is at 8500 15400 26000. This is at 10750 17500 28200. Now these are all in centimeter inverse. Now energy is directly proportional to the wave number. So that would mean in these cases the splitting is less, in these cases the splitting is large. So what could be the ligands? You have OH minus N3 minus, Cl minus I minus. Okay, so I would say the best answer for this is water and ammonia, which is given in your option number B. Cl minus I minus is not going to make so big a difference because both are very weak field ligands, and at the same time OH minus and N3 minus are also not going to make a very big difference, and it should be actually the other way around. OH minus N3 minus is a pseudohalide, so that would not be very good, it will not be a strong field ligand. Okay, the next question we have is from June 2017. The question says, consider the following statements for octahedral complexes. You have CrF6 3 minus and CO oxalate 3 minus. And the C is Cr ethylene diamine 3 plus. Their DD transitions are given in this form. Okay, so the DD transitions are given in the correct form: fluoride, oxalate, ethylene diamine. This is the order of the strength of the ligand, and that in the same way should be the absorption for the DD transitions. The values for the DD transition that is given. So it's true. So statement A is correct. Their spin only magnetic moments are same. We don't know that. Two of them have optical isomers. So yes, two of them have optical isomers, specifically ethylene diamine and oxalate. So they have optical isomers. So C is also true. Now all of them show John-Taylor distortion. Okay, so will they show John-Taylor distortion? They are all in +3 state. No, they will not show John-Taylor distortion. That means option A and C are true, which is present in option A and B, but B also has D, so that is removed. Your correct answer is option number A. Okay, so the next question is from June 2017. And the question says, match the following. You have complexes of water, ammonia, and ethylene diamine. The colors are blue, green, and violet. Absorption maximum are 675. 565, 615, all in nanometer. Okay. So how do you do this question? Now, let's first write them down in the order of their splitting strength. So this is the order. So that would mean, since this is in nanometer, the order should be exactly opposite. For the absorption, so that would mean En would have 565, CH3 will have 615, and water should have 675. Okay, now about the color. From violet to red, the wavelength decreases. So that would mean this should be violet, this should be VBG, VIB. Okay, so this should be B and this should be G. So this should be the answer. So you should have For A, you should have you have for green, which is your 2, and 675 is your X, and then for B you have blue, which is your 1, and 615 is your Z, and then C you should have violet, which is your 3, and you should have Y. So that is given in A2X, B1Z, C3Y is option number A. Okay. The next question we have is from GATE 2018. The question says the lowest DD transitions of the complexes follow the order. You have CR. Okay, so again I'm writing only the ligands: water, ammonia, and cyanide. Lowest energy, so that obviously will be water followed by ammonia followed by cyanide, which is given in your option number A. Very straightforward questions, and these type of questions were very repetitive earlier. Now they don't really come. So these are the questions till GATE 2018. Now I'm going to discuss the questions which have come after that. So there is only one question from December 2018. After that, there were no very straightforward questions from the charge transfer, or from the electronic spectra or selection rules. There are questions from charge transfer, there are questions from orbital diagram, which we'll see in the coming lectures. So the question says the correct order of the intensity of the DD transition in the complexes of 3D metal ion M2+. So what are the complexes you have? Cis MH2O whole 4 Cl2, and you have trans MH2O whole 4 Cl2, and then you have MH2O whole 6. Now if you recollect the laboratory selection rules that you had, now the laboratory selection rules gets relaxed in those cases when there is a loss of the center of symmetry. Now in this case, this is perfectly octahedral, right? So there is no loss of there is no loss of center of symmetry in this case. So that means this will be the lowest. Now in case of trans and cis, okay, intensity, okay. Now in case of trans, the structure would look something like this. You have water and you have Cl. Now only in the case of asymmetric stretching of the two Cl bonds, there will be momentary loss of the center of symmetry, and in that case the transition will be allowed, DD transition will be allowed, and there will be some intensity to it. Now in this case there is no chance of, there is very less chance of any kind of DD transition, so it has least intensity, followed by this which has some intensity provided there is an asymmetric stretch. Now in case of a Cl, the structure is this. The center of symmetry is itself destroyed now. The center of symmetry does not exist in this particular molecule. So that means it will have highest intensity, because the Laplace selection rules are not valid here. So the DD transition will occur favorably. That means they become allowed, and it will be the largest for this. So this is given in your option number A. I mean, it should have been the other way around. The symbol should be this followed by this. So option number A, and this was actually the correct answer. So that's all that is there to discuss from the electronic and color spectra. Electronic color spectra, the laboratory selection rules, spin selection rules, and the questions. The next major part from the spectra is charge transfer spectra, which I'll discuss in the coming lecture. And then we'll also, in the same lecture, we'll also discuss the questions that are there from there. A good amount of questions have come in NetGate and TIFR. By that, we'll be done with the one major part of the molecular orbital theory. Followed by that, we'll start the organ diagram and Tanabe-Stoyanov diagram. With that, half of the coordination chemistry will be done. Then we'll move on to magnetism. In case there is any difficulty in understanding any of the questions and understanding any of the concepts, you can always put them down in the comments. I'm really thankful to a lot of my viewers who have often pointed out certain mistakes that I do while discussing. I'm really sorry for that. I'll try to keep a check on that as I don't make many mistakes, and thank you that you point them out. I'll in those videos I'll try to add some of the other notes at that point of time so that the whoever is watching it can get the correct information. So see you in the next lecture.